Hi friends, so this is the second chapter of fluid mechanics, that is pressure measurement. So first we have to understand what is pressure. So it is the normal force exerted per unit area in the fluid. Okay, suppose there is area, that is area A, and consider there is a small elemental area dA, and force is acting normal to the surface dFn. So this is the normal force. So dFn is the normal force. So pressure, the definition of the pressure is the normal force exerted per unit area in the fluid. Okay. Now, so here, so this is the normal force Fn. Fn is the normal force normal to the surface, and there is a dA. This is the small area, and Ft, that is the tangent to the surface, tangential force. Okay. So if you want to calculate the normal stress, we know that sigma, that is equal to Fn by dA, and if you want to calculate the shear stress, tau, that is equal to Ft by dA. Okay. And pressure, we know that limit dA tends to 0, so area dA tends to 0 dFn by dA. And what is the unit of this pressure? That is Newton per meter square. So let's try to understand what is pressure. So it is the normal force exerted. It is the normal force exerted per unit area in the fluid. As per Pascal, the intensity of pressure is same in all direction. That is zero shear stress, static pressure. So this is very, very important. Okay. So the intensity of pressure is same in all direction. That is zero shear stress. Means it is a static fluid. The pressure is the scalar quantity because same intensity in all direction. The pressure is compressive in nature and analogous to compressive stress, that is negative normal stresses. So Pascal law is valid for compressible and incompressible, viscous and non-viscous fluid, but the fluid must be in rest. So this is very, very important. Pascal law is applied when the fluid is rest, not in motion. It is applied for compressible, incompressible, viscous, non-viscous fluid, but it must be at rest, and the ideal fluid or ideal flow. Okay. Now, so consider, so this is the area. This is a small elemental area dA, and here there is angle theta, and if you want to calculate the area of this surface, so it will be dA1, so dA cos theta. So dA is the surface normal to this, so angle, so dA cos theta. So this new area should be dA1, that is equal to dA cos theta. Okay. So suppose the fluid, here the fluid is rest, and the pressure is compressive in nature. So here, and rest, that is why tau, that is equal to 0, and that is the symbol for static fluid. Okay. The fluid is in static condition. Okay. Now this is the small elemental area dA, and the force, normal force, that is dFn. So we know that Pn, normal pressure, that is equal to dFn by dA, normal force by area. Okay. Now if you want to calculate at some angle, if you want to calculate the pressure P theta, that is equal to dF theta by dA theta. So this dF theta will be dFn, and the angle is theta, so dFn cos theta. So dF theta, that is equal to dFn cos theta divided by dA theta. Here also the dA cos theta, like this. So here the area dA dA cos theta. So here dA cos theta. So cos theta and cos theta cancel out. So dFn by dA. So P of theta that is equal to P of n. Okay, normal pressure that is equal to pressure and at any angle. Okay, so that means pressure intensity of pressure is same in all direction. Okay, now for solid we know the here we understand that what is the difference between solid and fluid. So for solid there is a normal stress is acting. This is the x axis, this is the y axis, and this is the z axis. So normal stress is acting like this, sigma xx, and here there is sigma yi and sigma zz, and there is a shear stress also acting in that direction also. Okay, so if we write all the stresses in matrix, this will be sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz, and you can draw Mohr circle. So in strength of material we read the Mohr circle. So strength of material, if you see in the basics on strength of material, you understand that what is Mohr circle. Okay, so for state of stress in static fluid, tau that is equal to 0. Static fluid means tau that is equal to 0. So here the pressure will be minus sigma because compressive in nature. Okay, and the matrix form that will be minus p 0 0 0 minus p 0 0 0 minus p. And for Mohr cycle this will be a point, there is a wall stress and shear stress and normal stress, and for static fluid the stress is the point. Okay, the state of stress is the point. So here this is minus p. Okay, so this is the Mohr circle diagram of the static fluid. Okay, now for free surface, tau that is equal to 0. Okay, so here this is the normal force and Fs is the surface force. Okay, Fn is the normal force and Fs is the surface force. So Fs equal to 0. So because here the force is 0, so Fs 0 means F cos theta that is equal to 0. Okay, so theta, so this is phi, so phi would be 90 degree. So the necessary and sufficient condition for a surface to be called as a free surface if shear stress acting on it must be 0. So this is very very important here. If the shear stress acting on it must be 0, this is the necessity and sufficient condition for a surface to be called a free surface. Okay, now application of Pascal law. For hydraulic lift we use the Pascal law. So here this is one system, and here this is the large diameter ram is there, and there is a small diameter plunger is there, and F is the force which is acting above the plunger, and W is the force which is acting above the ram, and inside that there is a fluid. Okay, now as per Pascal law, the pressure intensity of pressure is same in all direction. So here the pressure that is equal to force per unit area, so W by area, W by capital area, and here the F by small area. So W by F that is equal to A by A. So from here A, we know that A greater than A because this area is larger than this area. So W must be greater than F. So this is used in hydraulic lift. So now same here, this is the initial position of the plunger. This is the initial position of the plunger. Okay, and area is A1, and initial force is not changed, force is F. Okay, So now if the piston, the plunger move del x downward direction, consider this is the final position, and the volume change, the volume displaced volume, that is V1. Okay, the same volume must be up here, because the volume gets, because here the volume is, this is not the deformable body, so only this body can displaced. So here this is the initial position of the piston or initial position of the ram. So this is the initial position. So due to this V1 displacement, so that's why the initial position is changes to del y location, and this is the final position. So from here V1 must be equal to V2. So from here delta x, that is equal to A by A into delta y. So if you want to calculate the work done, that is equal to work done for this case F into dx, so delta x. So F into delta x, what is the value of delta x? That is A by A into delta y. So F into A by A into delta y. And if you want to calculate work done for this case, W into delta y. So W into delta y. Delta is the displacement from the initial position to the final position at ram location, and this is the plunger location. So this is my handwritten notes. You can download it from the description. Thank you.